Testing, testing. Oh, it's going now. Okay. Try that one more time. Show caption. Oh, there we go. All right, can we focus, please, guys? We have lots to do. So the first thing we're gonna be talking about today is it's actually continuation of lecture 4. I don't think we can finish it today, but we'll do as much as we can in 45 minutes. We're gonna start by talking about this concept of tonicity. This will definitely be on your test, so please pay attention to the meaning of it and understand it. Will help you, get the answer correctly on the upcoming test. So tonicity is talking about how a solution is going to change how the cell is going to turn out in a solution. It might get bigger, it might get smaller. By the way, the note is gonna be like this, okay? Just leave it as portrait, and then we're gonna have 3 cases, 1, 2, and 3. Okay, we're gonna do some drawings here. We're gonna have some explanation here, and then some more drawings, okay? It should fit on the whole page. All right, so case 1. Are we ready to go? Ready?
Yeah.
Yeah. Case 1 is isotonic. Isotonic. Isotonic means the solution has the same concentration as the inside of the cell. So let me draw this out for you, and then I'm gonna write it out for you as well. Imagine we have a beaker. A beaker is just like a container. And then I am actually gonna draw 2 beakers. 2 beakers. Okay. In the first beaker, we're gonna have an animal cell. Okay. Now, of course, this is not to scale. If you put an animal cell in a beaker, there's no way you can see it without a microscope. Even with microscope, you probably can't find it. Okay? It's really small, right? So that's an animal cell. And then in our second beaker, we are going to put a plant cell. And plant cell, they are more rectangular in shape. They are more rigid because of the presence of cell wall. Okay, so we have the animal cell here and the plant cell. So what does it mean? Leave some space. We're going to draw more stuff here, okay, and then we can write the description here. It means the concentration, we use square bracket to represent concentration. The concentration of the solution is equal to the concentration of the cytoplasm. Cytoplasm is the inside of your cell. Square bracket means concentration. Okay. So if I use dots to represent it, okay, we're gonna have some dots right here. Okay, and the inside would be about the same. Oh, I just remember I missed a few slides on the PowerPoints. It's okay, we'll go back to it. We just understand this first. Okay, so this is isotonic, right? The concentration of the solute in a solution would be the same as the concentration inside the cytoplasm. Now, because of the few slides that I just realized I missed, there might be some gaps here. But the thing to remember is we are focusing on the movement of water here. Okay, we're focusing on the movement of water and not the purple dots. Okay? For our discussion, the purple dots represent the solute, which is like salt, for example, and they are not able to move through the membrane. Okay? So the only thing that can move is going to be water in this case. Because the concentrations are the same on the inside and on the outside, then the amount of water that's moving into the cell is actually going to be equal to the amount of water leaving the cell. And that shouldn't be difficult to understand because everything is balanced on the inside and outside. So the cells are not going to be necessarily gaining water or losing water overall. Water is still coming in, it's still leaving, but they cancel each other. So there's no change in cell volume. All right, so let me write this down for you. Rate of water entering the cell is equal to the rate of water leaving the cell. So what happens? Overall, there are no net water movement. No net water movement. Now, if you're having trouble visualizing this, I'll give you an analogy here, okay? And you can choose to draw it or not. It's up to you. Okay, so we have a tab here, and we have a basin. And so I'm going to fill up the basin with some water first. So what happens is there's a leak in the basin. Okay, so water is going to be dripping out, okay, from the bottom. But if I turn on the tap and I let water come in at the same rate, then they are going to cancel each other's effect. What's going to happen to the water level? Exactly, right? It's not going to go up. It's not going to come down. It's just going to stay the same because rate in equals to rate out. And that's what's happening when you put a cell in an isotonic environment. Water will be coming into the cell, and at the same time, water will be leaving, and the two cancels each other out, and the cell volume does not change. That's isotonic. Does that make sense? Any questions? Okay, so what's going to happen? Well, if it's an animal cell, okay, it's going to be quite happy. No change. Okay, it's going to look exactly the same. So this is happy. Happy. For the plant cell, okay, also no change. Going to be exactly like before. But it's not the ideal situation for a plant. Okay? They're like, meh, it's okay. I don't mind it, but it's not the best. Okay? Because plant likes to have water. Right? So they can store it and they can do photosynthesis, right? So in an isotonic environment, it's surviving. It's like if you forget to water your plants for a couple of days, and you see it kind of, not stand up as much, right? It kind of wither a little bit, maybe, curl down a little bit. That's the situation with the plant. It's not ideal, but it'll live. Okay? That's the easiest scenario. Are we all together? Okay, this will be on your test, so make sure you understand it. Okay, so there are two more scenarios that I have to go through, but like I said, I just remember you guys are at a different pace than my other class. So there are a few extra slides I have to go through before I tell you the other two cases. All right, so let's back up a little bit further. Can you guys not throw those names all over? Please take it with you and then, find a garbage can. Thank you. Okay, first thing here is diffusion. Diffusion is the concept of molecules being able to spontaneously on their own spread from an area of high concentration to areas of low concentration. So in this example, if I have a flask of water and you drop some dye into it, the dye is highly concentrated, right? And then it will on its own spread out until the whole solution is blue. it will do it on its own. You don't have to, you know, swirl it or anything. You could, if swirling it's gonna make it, you know, diffuse faster, but on its own, it's able to do it without any kind of intervention. Okay? It's the same thing. If I take like a Febreze air freshener, I spray it here, right? Soon you'll be able to smell it at the back. And that's another example of diffusion, going from area of high concentration to area of low concentration. Now, there are different factors that will affect the rate of diffusion. It's going to happen, but how fast is it going to happen will depend on several factors. Okay? Number one, the size is going to matter. If it's really big and bulky, it's going to take longer for it to move around, right? Compared to smaller ones. So generally, smaller molecules will diffuse faster than larger ones. So over here, we have oxygen, which diffuse quite fast. And over here, we have a big one. It's glucose, and that will, you know, take longer time to diffuse. The second factor that affects the rate of diffusion is temperature. If it's hot, then things tend to move a little bit faster compared to when it's colder, okay? An example of this is like on a hot summer day, if it's garbage collection, you can smell the people's garbage on the road, okay? Because very hot, all those unpleasant odors just gonna diffuse all over the place. Not so much in cold winter days, but you can barely smell anything. The temperature is going to affect how well it spreads, how fast it spreads, rather. Another factor is called the steepness of concentration gradient. I told you already, things will naturally go from high concentration to low concentration. Just like, you know, if I have something at a high point and I let go, it's going to drop to a low point, right? So over here, how fast that happens depends on the two areas you were talking about, right? For example, in the top picture here, on the left side, there are a lot of these red dots. So, you know, I'm just going to make up a number. Let's say this is 100%, and there's nothing here. So that's 0%. We are talking about a difference of 100. So they will quickly want to go over to the other side. Whereas over here, we have about, just making it up, say 60% and 20%. So the difference is not as great. They will still go over, but it's not going to happen really quickly. Do you understand? Right? Think of a very crowded plaza or something, okay? And then there's like empty space. People are going to want to go there quickly. Right? But if the other side already has some people, then maybe, you know, some will move, but not everybody. So with how fast is it happening is going to depend on the difference between the two locations you're talking about. The greater the difference, the steeper the concentration gradient. Okay? Another way to help you understand is, you know, like think of a ball going down the ramp. Okay? If I let go of the balls A and B, which one's gonna get to the bottom faster? Yeah, because it's steeper, right? And so that's what this is. If the yeah. You don't have the same slide. You don't have the same slide? Oh, interesting. What kind of slides do you have? You'll be here, right? Yeah, it's early on because I missed a few. Yeah, sorry. Okay, another factor is the charge of the particles. I hope you know light charges repel each other. And so if you put a lot of positive close to each other, they will move away much faster than if they are all neutral. Okay, so the charge is going to play a role in how fast they spread out initially. Okay. Yeah, those things are always falling out. Don't worry about it. Just leave it be. I have a whole play of them here. Look, see? Leave it here. Okay, I'm going to explain this next part here. This is where it can get a little bit confusing. Now, I know you cannot do this on your note, so maybe just draw it elsewhere. I'm gonna cheat a little bit here. All right, so write it elsewhere. So I'm gonna explain osmosis for a bit. Okay. So we're gonna draw a special type of tube. I mean, it doesn't have to be a tube, but most pictures involves some kind of tube. So I'm gonna do the tube. Okay, and it's a U-shaped tube. All right. Now at the bottom of the tube, I am going to put a special membrane. This membrane only allows water to pass. Nothing else. Only allows water to pass. Now I'm gonna fill the tube up with some water. I'm gonna fill it up to the same level. There we go. So far, so good. Then I'm gonna dissolve some solute into it. Okay, and I'm gonna put some here, and then I'm gonna put some here as well. Now you see, I deliberately draw the red circles very big, and this membrane only allows water to pass. So the red balls is not gonna fit. You understand that? The red circles cannot pass through, even though they want to. Because things naturally wants to go from high concentration to low concentration, right? The red wants to move, but they can't because they are blocked by the membrane. That is important to understand. So just for reference, I'm gonna put on the left side, high concentration. Square bracket means concentration. This is low concentration. In case you don't understand the concept of concentration, right? Like think of a glass of water and then I add like 3 spoons of salt in it, then it's very concentrated, right? Compared to like just a few pinches of salt. Okay. All right. So here is the thing that most people have trouble understanding. You already should know the red things wants to go to the right, but I'm telling you they can't because they are blocked by the membrane. So the only thing that can move in this situation is water. So I want you to tell me, do you think the water will A, move to the left, or B, move to the right? Just think about it first. Which way will water move? Not the red dots, because the red dots can move. Which way will water move? Yeah, hold on a second. I want to tell you something to help you visualize this, okay? Imagine taking a spoon of salt and put it in your mouth and you hold it there for 30 seconds without swallowing. Think about what would happen and then apply that to this situation. Which way will the water move? 1, left. 2, to the right. Okay, show me what you think. Okay, good, good. Yes, yeah. Okay, not quite. Yeah. Okay, yes. Which way? 1 or 2. Good. Okay, okay. Anyone else? That's good. Okay. Yeah, good. Okay, the correct answer is water will move to the left. Okay, water will go to the left. Think about the example I try to tell you to visualize. If you put the salt in your mouth and you hold it, what's gonna happen after a couple seconds? It's gonna start watering right your mouth, right? The salt is essentially sucking the water out of your mouth, right? So similarly, because there are higher concentration of solute here of the salt, it's gonna draw water towards that side. And this is the core concept of osmosis. Yeah.
Is that because this side is a little bit higher in the volume?
No, the volume are the same, okay, same level, right?
No, I mean
Concentration.
Yeah, concentration.
That's right. This is high concentration, and the water will be drawn to that side. Okay.
I just want to check. Am I thinking?
Yeah, sure. Okay. So I'm gonna type this out. It's probably better for you and for me. Okay, so water will be drawn to the left side. Okay, listen, guys, this is important for you to understand so that you can understand the rest of the lesson. Tell me, as water moves to the left, what's going to happen to the concentration here? Is it going to go up or down? Down. You're diluting it, right? Okay. So the concentration on the left will decrease. What about the concentration on the right? That's right. So as the water is leaving, the volume goes down here, and it's gonna get more concentrated, right? Like if you cook, it's like reducing a sauce. Right? You steam up all the water, and you end up with a thick, nice sweet sauce or something. All right. So that's what's happening. So this will continue until the concentration on both sides are equal. Okay. So water level is going to go up here, and then water level is going to go down. Okay. That's because of the membrane here, right? That's the key thing. If the membrane lets everything through, then the red's going to come over, and then, it will get all mixed up. Right? Are we okay? Any questions? Yeah.
It's a solution cannot move, right? Why put it there?
What? Since what cannot move? Yeah, the solids are there to allow, like to cause. Why do I put the dots here? Like it cannot move? Yeah, it's because of the dot that causes the water to shift. If I don't put the dots there, then it will be the same, and then there will be no water. That's keeping to remember.
How would they end up there in the first place, though?
The solid? Oh, you will have to.
Oh,
Yeah.
okay.
Okay. Now, I'm gonna apply this concept to tonicity. Okay, tonicity, which is what we were talking about before I realized I didn't teach you this thing yet. Okay. So tonicity, once again, is the capability for a solution to change the cell's volume by altering the movement of water. In the first example, we did isotonic. Okay, so I'm gonna go through two more examples with you, and then I'm gonna let you go. All right, the end is near. Just hang in there. Number 2, it is called hypotonic, and I want you to write the O really big because it's gonna help you remember what's gonna happen. Okay, so I should probably say isotonic solution here. And here is hypotonic solution. Okay, for those of you who are not copying this down, make sure you go home and then write the notes, all right, because it's going to help you understand what's going on. So let's draw the cells again. Okay, this is the beaker, okay? This is not the cell. This is just the beak, like a glassware to keep the cell in. And at the top, we're going to put an animal cell. Animal cell. And here we're going to put a plant cell. For a hypotonic solution, the concentration of the solution, like the surroundings, is going to be less than, I'll just use this symbol, less than the concentration of the cytoplasm. Hypo means lower. Right? When someone has hypothermia, their body temperature is too low. So hypotonic means the solution concentration is lower than the cells. So I'm gonna use these purple dots again, red dots, whatever, doesn't matter, up to you. Okay. Not a lot on the outside, but a lot on the inside. So, because of the cell membrane, the purple dots are not able to move freely, just like that special membrane down at the bottom of the U-shaped apparatus, right? So here, the purple dots, they can't move. The only thing that will move would be water. So I want you to think about this again. Is more water going to be going into the cell or out of the cell, based on what I taught you? Into the cell? Yeah, I hope you guys all understand that, right? Because that's where the salty stuff is. Right? So you will have water coming in. Water will still be leaving, but just not as much. Okay, same thing, water leaving. And then you got a bunch of these water coming in. So the rate of water entering the cell is greater than the rate of water leaving the cell. So what's going to happen to our cell? Is it going to get bigger, smaller? What's going on? Yeah, it's going to get bigger, right? So net water movement. Before, there was no net movement. In equals out. But now, net water movement would be into the cell. Into the cell. And so I'm going to draw the basin again here to help you understand. Okay, you're going to have the water. Try that one more time. You're going to have the water. And then it's leaking at the bottom. But now, in this scenario, it's like if I turn on the tap to the max. So lots of water coming in. Not as much leaving. What's going to happen is the water level will rise and eventually overflow, right? So that's what's going to happen with our cell. You have so much water coming in, but not enough leaving. The cell will get bigger and bigger and bigger, and eventually it will pop. Okay. So for an animal cell, it is going to get really big and then it's going to pop. Okay, we call this lysis. Lysis is to break, right? You learned that before. Burst. Okay. So obviously this is bad news. It's dead. Okay. And then over here, for the plant cells, this is when you water your plants nicely, they are happy. And then, do you remember? I mean, you label it on the quiz if you got the plant cell. You remember there is a big thing in the plant that stores water? What is that thing? Yeah, that was the thing, right? So it's gonna fill up with water, and the plant, of course, has a cell wall as well. So the cell wall is gonna protect it from bursting, and the full central vacuole is actually gonna push against the cell wall, and it creates what's called turgor pressure. And this pressure allows the plant to basically stand up really tall. Okay. And then all the leaves are going to be like all open up, right? Nice and plump. The plant loves it. Okay. Plant prefers to be in a hypotonic environment solution, but not us. Okay. So that's how you can remember it with a big O. Right? The cell gets big. Okay. Hypotonic. Yeah. Where? Sorry. Turgor. Turgor. Yeah, sorry. So we're gonna have one more scenario, which is hypertonic. Hypertonic solution. Turgor. Yeah. Okay, almost there. So once again, we have the animal cell, and then we have the plant cell here. This time, for the hypertonic solution, it is the other way around. You have more solute outside, and then not so much on the inside. So what's going to happen to the water movement? Is more water coming in or leaving? That's right. Water still coming in though. All right. Just like more is leaving. All right. It's like, we're still making money from our work, but seems like we're spending a lot. It's like that, basically. So then the concentration of the solution in this case is greater than the concentration of the cytoplasm. And the rate of water moving out. Sorry, I'm just going to use the same order here. Oh, that was entering. So let's do entering first. Rate of water entering the cell is less than the rate of water leaving the cell. Which means the net water movement is going to be out of the cell. Out of the cell. Okay, here's the tab again. And I think you know what's going to happen. Super big hole at the bottom of the basin, leaking all over the place. But water coming in is just normal. So eventually the water level will go down, right? So what's going to happen to an animal cell? That's right. How do you know that? Is it in the notes? Or you just happen to know?
Well, I think I don't.
Very good. That's the right answer. Okay. Plasmolysis. It's going to shrivel up. Okay. It's going to shrink like a raisin. Okay. So it's not going to kill us. Right? But it's not the best. Okay. This is like when you are dehydrated. You're not drinking enough water. Then your blood becomes too concentrated. And then the cells start to shrink and shrivel up. You'll be fine as long as you drink soon. For the plant cell, it is not good. Okay. It's also called plasmolysis. Okay. But they are very shriveled up. Okay. The cell membrane will still be, sorry, the cell wall will still be there, but the cell membrane is gonna basically like detach and pull apart from the cell wall, and it's like shriveled up on the inside. I like shriveled up on the inside. And that's when you forget to water your plant for a long time, okay? So it's starting to look really sad like that. Okay? And it's gonna basically start falling off. The leaves are gonna start falling off and it's gonna die unless you water. So that's tonicity, okay? There will be 5 mark question on the test that requires you to maybe draw some of these, maybe describe some of it. So please make sure you do that. Now, before you go packing, I just want to show you a few more slides here, and then we're done. So these are red cells, okay? That's what they're supposed to look like normally. This is when they are in a hypotonic state, getting really big, it's about to pop, and then this is when they're shriveled up. So if you become a nurse or a practical nurse, right, or like if you work in healthcare, a lot of times you might have to give IV to your patients, right? Okay, intravenous fluid. Just do what's like, and I'm gonna safely go. So for healthy patients, you know, who otherwise do not have any complication, you want to give them isotonic solution. Okay, you want to give them solution that their cells are used to, so you're not going to be like popping their red cells and whatnot. So a normal solution is 0.9% normal saline, and it's used for rehydration purposes for people who may be bleeding a lot, or if they're vomiting or suffering from severe diarrhea or something. You want to replenish the fluid. Sometimes though, you want to give them hypotonic solution. Okay, so hypotonic, you can see is 0.49%, which is half of the normal concentration. And this is used for treating hypernatremia. That's a big word. Emia means in the blood. You guys know what element natrium is? Sodium. Very good, because sodium is Na, right? Okay. And then hyper. That means it's too much sodium in your blood. Right? If you are sweating excessively, right, and then you are not replenishing your water, then they might need to give you 0.45 hypotonic saline to dilute your blood a little bit. Okay. The other one is 3% hypertonic. This is very rare. I asked my sister, she's a nurse for like 15 years. She never used this before, okay? But this is the opposite. If someone has too low of a sodium in their blood and you need to like quickly bring it back up, then you will have to use 3%. Okay. One last thing, one last story, and then you can go. Do you guys know like the video game console, like the Wii, W-I-I?
Yeah.
Yeah, it was like a long time ago, right? Like what, 15 years ago when it came out. And it was such a hit, right, back then, because it was like considered as an innovation and whatnot. So there was this radio station that hosted a contest called Hold Your Wii for a Wii. Yeah, this is for real, you can look it up. Hold your Wii as in like hold your urine, right? W-E-E, and then to win the Wii. So the contest goes like this. The contestants have to drink a lot of water, and then they have to hold and not go to the bathroom. And whoever did that would win the console. Okay, so this lady won. She was able to drink a lot of water, not go to the bathroom, and she won the gaming system. Right? but then that afternoon she died in her apartment. Okay, so don't be mean.
Sorry.
Well, based on what we talked about, what causes her to die? Too much what? Okay, yeah, and what did you say? Too much water, yeah. Basically, too much water makes her system hypotonic, right? And when it's hypotonic, what's gonna happen to your cells? They're gonna burst, right? Okay, so that's one of the reasons why drinking so much water in a short period of time can cause death. It's called water toxicity.
So did we get sued?
I actually don't know. I didn't follow up. Maybe you can sue anybody with anything. All right, that's it. All right, please read the lab. I'll see you on Thursday for it.
Yeah.
Yep.